Hi, so I'd like to talk to you about hybrid SBI or how I learned to stop worrying and learn the likelihood. And this is the work done with Oliver Philcox here at Flatiron and Columbia. Okay, so far in cosmology, our workhorse tool has been like analytic methods such as perturbation theory and EFT of LSS. And this has been highly successful in the last 2 decades to model lower order clustering statistics such as power spectrum, bispectrum, uh, and linear and quasi-linear scales. And broadly, the way it works is that we have these analytic integral equations for modeling these statistics. We use them to get a model prediction. We have good reasons to believe that Gaussian likelihood is sufficient on these scales. So we have an explicit likelihood form, and we combine these two together to do the parameter inference and get constraints on cosmology parameters, right? In the future, what we would like to do going ahead now with the extremely rich data that we are all gathering is that we would like to go beyond these 2 or 3 point analysis to higher order statistics, say some learned neural statistics, which we believe to be optimal. And we would like to push to smaller scales, which are getting increasingly signal to noise dominated. The challenge to do that with the standard analysis, the way we have been doing it, is that we need theoretical models for all of these statistics. There is a whole range of these statistics for which we'll need to develop these models. And for some, for example, for like learned neural statistics, it's possible that we'll never have these kind of theoretical models. Even for the existing statistics, perturbation theory and effective field theory breaks down on small scales, so we cannot push to these scales with them. And finally, including things like survey systematics gets increasingly challenging to include in the theoretical formalism. So there is a growing understanding that computational modeling is easier, probably arguably more accurate in some regimes. And so we would like to use simulations to do the analysis. So that's broadly the motivation for SBI. And I would not go into the details of like how it works, but broadly what you end up doing is that you generate training data set, which is simulations over a broad range of parameter space. And then you use them as for training either a neural likelihood estimate or a neural posterior estimate in this case, right? And you use normalizing flows for that. And we have done this on data now. For example, this is just one example from SEMBIC collaboration, which used 100,000 BOSS South Galactic Cap galaxies, use statistics like power spectrum, bispectrum, wavelets, CNNs to do the analysis to get inference. And broadly, the takeaway was that, like, yes, SBI allows us to use higher order statistics. It allows us to push to smaller scales. And both these things allow us to improve the constraints. So the question we wanted to ask was like, okay, is this good? Can we now just go ahead and do it for any of the future surveys that we are collecting data for? And the answer is no. And to look at that, let's consider what the next generation of surveys would be like. So if we consider surveys like DESI, LSST, Euclid, or anything, we require simulations which have much larger volumes because these will be like multiple times, 10 to 8 times larger than the current BOSS surveys. We need better mass resolution because we'll be probing fainter objects. And we'll need increasingly accurate forward models because both the signal to noise of your data will be improving, and you'll be using higher order statistics. And to get both that, you need increasingly accurate forward models which are compatible with both these two things. On the flip side, if you look at the current computational landscape that we have, the best simulation suite we have for doing this SBI stuff is Kyoto Latin Hypercube, which is great, but it is not sufficient. It required 10 million CPU hours to run, I think, approximately. But I would argue that it is small in volume. It is only 1 gigaparsec, which is smaller than even the BOSS survey. And that's why SEMBIC only did South Galactic Cap and didn't analyze the full BOSS survey in the first place. It is coarse resolution. It is only 1 megaparsec. It has only 5 snapshots. So you are kind of restricted to doing HOD kind of things. And you cannot use more accurate galaxy models in this case. So I would say that it is computationally prohibitive to scale to the next or even current surveys for the BOSS surveys for doing SBI. And in that case, the question is, how do we scale to the upcoming cosmological surveys? So to look at that, let's go back to the motivation for using SBI. The motivation was that we wanted to use higher order statistics, which can extract more information from the non-Gaussian scales. And we wanted to use the statistics which we cannot model analytically, right? So if you think about this, then on the larger scales, we don't need SBI because on the larger scales, the density is Gaussian. It can be modeled using perturbation theory and EFT. And there have been recent works which show that the traditional statistics like power spectrum and biospectrum are kind of close to optimal on these scales. So you can use wavelets, you can use CNNs, but if you're on the linear and quasi-linear scales, you're not really going to gain that much out of it. So the goal of hybrid SBI, or the motivation of the hybrid SBI, is to combine perturbation theory on the large scales with simulations-based inference only on the small scales in this case. And the way it kind of works is that if you imagine that your data vector from your observations is like X, and it can be split into two components, a large scale component, which I'm referring to as XL here, and a small scale component XS, then you can decompose your data likelihood exactly in these two terms, which is the likelihood of the large scales and likelihood of the small scales condition on the parameters and the large scale statistic in this case. So then the framework basically is that on the large scales, we'll use perturbation theory or EFT, and we'll be using any classical statistic which you can apply perturbation theory and EFT on, which for us is mostly power spectrum and biospectrum. And the small scale likelihood distribution here will be learned using simulations-based inference. So you can use any statistic of your choice on the small scales, power spectrum, biospectrum, wavelets, or you can learn the neural summary statistics in this case. But the goal is that you want to learn the small scale statistic only from the small sub-volumes, which are now being simulated at the highest fidelity that you want, without having to simulate the entire survey volumes at the full fidelity in this case. So that's broadly the motivation, the formalism. But there are obvious challenges because there are no free lunches. So there are two key issues with this. The first is that to learn the likelihood of the small scales condition on the parameters and the large scales, you need to develop new customized simulations because now your small scale statistic depends on the large scale statistic. These two are correlated. And so you need to come up with a way of simulating the correct large scale universe from which that small scale statistic has come from. This is not as crazy as it sounds because you have tools we already have tools around to do things like this. We have simulations like Escola, which evolve small scale and large scale separately. And you can use more high fidelity simulations on the small scales for this. We do zoom in simulations in galaxy formation all the time, which again, look at a small volume of the universe and then probe it with higher fidelity in this case. The thing is, we now need to develop these kind of simulations on cosmological scales for this. So this is not what this talk is going to be about. This is going to be a future work. This talk is about the second part of this, that now we also have super sample effects. So instead of estimating the small scale statistic in only a sub volume instead of the full volume of your universe, you kind of open the doors for like increased cosmic variance, and you'll have super sample variance. So your small scale statistic become noisier. So the question we wanted to investigate in this first paper was like, how much do you lose on the constraints because of these noisier small scale statistics? Does it completely wash away your constraints, or do you still gain something in this case? So to do that, we set up a toy example. We decided to use 3D dark matter density field as our observable and infer omega matter and sigma 8. We took the large scale statistic to be power spectrum up to k of 0.15. It is modeled with EFT, and that's basically the likelihood distribution for that. On the small scales, we used power spectrum and wavelet coefficients in this case. To train SBI, we took the Kyoto simulations, chopped it up into 8 small sub-volumes, and then used only these small sub-volumes to train the SBI algorithm and learn this likelihood distribution. So this is basically the result. In the blue, I'm showing you the results, what happens if you use only the power spectrum for this, which is what we would have done traditionally. The 3 different colors are different kinds of SBI. So the orange is if you would do SBI on the standard SBI on the full volume. And in the green and purple are the hybrid SBI if you use power spectrum and wavelets. So the hybrid SBI still outperforms the traditional analysis. You would see that you lose a little bit as compared to the orange line. If you compare the orange and the green line, you lose something, but that is because in the hybrid SBI formalism, you need to model over the CS square term in the which is the counter term for perturbation theory. But this is only for matter. For galaxies, you'll have to marginalize over things in both the cases for both SBI and PD. So you won't lose as much in that case. Okay, so this is the money figure. What I'm showing here is like how much do you lose the constraints if you simulate, if you use only one subvolume of the universe, or two subvolumes, or four or eight subvolumes in this case. Eight subvolumes is basically when you have essentially covered the entire box. So you should get close to what you would have gotten if you are using the full volume anyways. And one subvolume is when you have, factor of 8 gains in compute in this case. And on the left is the results for power spectrum. On the right is the results for wavelets. And you see that you lose about like 5 to 10% for omega matter, or 40 to 120% for sigma 8 with power spectrum, 20 to 50% for omega matter. But this is compared to using all the 8 subvolumes. If you compare it to the traditional analysis of power spectrum, which is the blue figure, you still gain much, much more, even by using just a single subvolume in this case. So the moral is basically, if you have enough compute and if you can simulate the entire universe, that is obviously the correct way of doing it, or not the correct, but that's obviously a better way of doing this. But even if you could simulate only a small subvolume, you still can make a lot of gains in this case. So yeah, that's my summary slide. I try to motivate, like HySBI is one of the most promising techniques to go beyond current cosmological analysis. I think most of us agree here on that. I wanted to highlight that we do not have the computational resources to actually do it going ahead with the surveys that the way we would like to. And I've proposed hybrid HySBI as an alternative as a realistic path for scaling it to the large surveys. I've listed some of the things that are required to do to able to do this on surveys to go beyond the proof of principle. The first and foremost is developing these kind of new simulations, which is what I'm working on now. The second part is like you want to treat the different nuisance parameters for observables like galaxy. Perturbation theory has bias and counterterms. HySBI has HOD parameters or SAM parameters, and they are not independent. You want to treat them simultaneously, treat them consistently in a joint fashion. And that's the work that's being led by Gemma, who is here on this. And thirdly, you need to figure out ways to include survey systematics, but because you're using simulations, that's probably not going to be that hard. Thanks.
Do we have questions in New York?
Very nice talk, Chirag. So this is focused on summary statistics. If you want to...
Not necessarily. You can use learned neural statistics. Like, so you can use your CNN on the small subvolume and extract like optimal summary statistics using that.
I see. But for the perturbation theory, if you want to do a field level thing for the counterpass and all these things, it's clear how to do these things?
For the perturbative part, you're still using power spectrum and bispectrum. And that's what I was referring to, the paper that I cited by Giovanni Cabas, who was at IS. And they showed that if you are only using data from the perturbative regime, then even doing the full field level inference kind of gives you basically the same amount of information as using power spectrum and bispectrum in the high signal to noise case, which is where we will be in the future.
Okay, but that's because you always cut on this kind of conservative scale.
Yeah, so the scale cut here is defined based on two things. First, you need PT to be able to model up to those scales, so you can't push very small. You also don't want the scale cut to be very large, because the smaller the scale cut, the less compute you need. Yeah, so there's a trade-off.
Let's give like a little bit more time and move to Paris now. Do we have questions in Paris?
Questions? There is no question. There is no hand raised. Oh, Ben is over there. And
hi, Chirag, very nice talk. One of the reasons to do these kinds of simulations is to include all kinds of instrumental systematics, surveys, selection effects, et cetera. And sometimes those are certainly easier to handle when you have access to simulations covering the full volume. Do you have any ideas for how to deal with them in the context of this hybrid approach?
The answer is not going to be very satisfying. It is the third point here on the slide, that we need to come up with ways. It might be easier for some kind of systematics. It might not be easier for the other systematics. So for example, I can imagine it might be easier for something like fabric collision, which is like a local effect. And you can just Monte Carlo to death on the small subvolume. Including survey masks might be trickier. But I'm not an observer, so that's why for the last part, I would really love to work with people who actually have hands-on knowledge about like how to do these in the real data in that case. Yeah.
Thank you very much. We are at the end of this 15 minutes and we need to be on time in this session. So let's move on to Pablo. If there are questions, please direct them to Slack.